1 times the second function, sine of xy. Plus, now I take derivative of the second function. Derivative of sine of something is cosine of it. So I'm going to cosine of xy. Chain rule times the derivative of what's in here. And I'm doing this with respect to x, so I'm treating y like a constant. So derivative of x times y should just be y. And then do not forget to finish off the product rule. Right? All of that was a product rule. So you have to go back and get that x from the product rule here. Any questions on that? We are done with that. Right? Okay, times, so we're going to multiply that times this now. dx dt, I'm going to put that right here, times, all right, dx dt. I need to take derivative of x with respect to t. So what's the derivative of this with respect to t? 2t. Nice, easy, clean, 2t. All right, plus now, so I've got this done. Plus, okay, partial of z with respect to y. So I go up to this one. I take derivative with respect to y, which we did earlier, didn't we? It was x squared cosine xy. That was a previous example. It was x squared, so look back in your notes there. It was x squared cosine xy. All right. That's this. Check. And finally, I need dy dt. Derivative of y with respect to t is just 1 over t. Derivative of natural log of t is 1 over t. Lauren, you got a question? You okay? Oh, you had a, okay. You look like you had a question. Someone else? No? All right. There it is, right? Yes?
So since we took the derivative of ln of t,
yes.
This is only valid for t greater than 0, right? Easy dt.
Well, it would have been a restriction back here, right?
Right, yeah.
Yeah, so that restriction carries in there as well.
Okay.
Yeah. So that basically inherits the same domain restrictions as this does. Does that always, that's a more profound question. Does your derivative always inherit the domain restrictions from the parent function? What do you think?
Well, how do you take derivative of something that's not defined?
Exactly. So it seems like it should. Is there ever a chance that it gets more restrictive? Like the domain of that derivative gets more restrictive than the original domain? There's an easy example of that. This is back in Cal 1. If you take f of x equals the square root of x, the domain of that is all values of x greater than or equal to 0. Right? That's the domain of that function. But the derivative of that function is 1 over 2 square root of x, and you cannot plug 0 into that, but here you can. So your derivative will always inherit the domain of the original function, but it could even become more restrictive than that domain. It is possible.
Also like an absolute value of x.
Yeah.
Like 0.
Yeah, so you actually, your domain of your derivative will always be some sort of subset of the original. Yeah. Okay, now at this point, that is our derivative. If we wanted to, we're just going to leave it like this, but if we wanted to, we can now replace all our x's and y's with these two functions. Everywhere I see x and y, x and y, x and y, x and y, I could replace them with these two, and what I would have is a function of t. It would just be ugly, but I could do it, right? Which would almost be back to what you said in the beginning. Like, why not just replace x and y here with these expressions and then just differentiate with respect to t from the beginning? We could have done that. I think in this problem you could argue a case for both. You could say, yeah, you know, maybe it would have been better just substitute in.
Is it going to come down to analysis to decide which is better?
Well, we're trying to generalize. So this is more about like what happens when we continue to add complexity. So let me make this a little bit bigger.
Some point where the substitution just won't work.
It just becomes too tedious to keep track of. So look at, I'm trying not to expose the whole tree, but I think I have no choice. Maybe I make this big enough that you can't see it. There we go. That'll be enough. So what if your z, what if your z is a function of x and y, but your x is a function of two other variables. So x depends on s and t, and the y depends on s and t as well. So I'm going to draw the tree here. I have z depends on x and y, right? So as of right now, there are only two partials down each branch, right? But see, x does not depend on one thing now. X depends on two things, s and t. And the y also depends on s and t. See the difference between this problem and the previous one? We have two branches down and at the bottom. So the first question is, what derivatives are even possible? Like, what can I ask you to tell me now? Like, find what? Like, what are the only things? Well, z ultimately depends on two different things, doesn't it? So the only thing I can ask you for would be a partial derivative, which means you would have to hold one of these constant. So one thing I could ask you here is what's the partial of z with respect to s? And that means you would hold the t's constant. Or I could ask you for the partial of z with respect to t, and there you would hold the s's constant, right? So I'm going to just get to an example. I want to skip over the tree because I don't want to develop the tree yet. So that would be a problem if it were presented to you. I think I'll try and copy this and bring it into... Yeah, let's do that. I think that'll be better. Give me some space to work with there. Okay. So let's say that was presented to me. All right, I'm going to start with a tree. Z. Z depends on x and y. X and y both depend on s and t, respectively. Once I draw my tree, I'm going to start labeling the branches with the derivatives. So if I go down the left branch here, this has to be a partial of z with respect to x, and then the other side partial of z with respect to y. What do you think about this branch? Another partial, right? Because x depends on two different things. So the derivative from here to here is a partial. Partial x with respect to s. This side would be partial x with respect to t. And then over here, partial y with respect to s, partial y with respect to t. See, I'm just filling out the tree. Questions on the tree? Questions why something's a partial and not a regular derivative? Now the two things I could ask for. Let's look at this one first. Partial z with respect to s. The way I do this is I figure out the parts of the tree that get me down to s, because the variable here is s. So here's my s's, right? Here and here. So to get to this s, I come down like this and then come down like that. So it's this piece and this piece. I multiply those two pieces together. That's part of the answer. And then I go to the other branch and I get myself down to s. So I've got to come down here and then come down here, right? And then I'll be there. So I'm going to multiply those two pieces. I take the two products from those branches and I add them together. And that's my derivative. The tree is just to help us keep track of everything, right? So the partial of z with respect to s would be, let's go down that left branch over there, partial z with respect to x times partial x with respect to s plus partial z with respect to y times partial y with respect to s. That's the first thing I would have to compute if I wanted to do this, right? Now, do you want me to work that out, or do you want me to write the formula for the other one right now? Work that one out, or go to this formula?
Work out the first
Want to work this one out?
Yeah.
Okay. All right, let's do this. The partial of z with respect to x first. Now the good news is we've done this, right? We did that previous. We're going to take the partial of this x sine xy with respect to x. What was it? Sine xy plus
xy cosine xy.
xy cosine xy? Thank you. Okay, that right there should be this, right? Done? Times. Now the partial of x with respect to s. So I go up to my definition on, here's the definition of what x is. X depends on both t and s. I'm differentiating with respect to s, which means I'm holding my t to be constant. So that t is a constant, derivative at 0. And then now derivative of 4s would be what? 4. Okay, so that's a 4. Boom, plus, okay, partial of z with respect to y. So you take derivative of that with respect to y. We've also done that already, haven't we? What was it, x squared? X squared cosine xy. Okay, so now I've done this. And finally, the partial of y with respect to s. That's kind of bad notation, but let me see. Y is equal to natural log, that's supposed to be natural log of st, like that, s times t. So if I want the derivative of that with respect to s, I treat t like a constant. So first things first, derivative of natural log of something is 1 divided by it. So 1 divided by s times t times, now you take the derivative of what's inside, but you're doing it with respect to s. So that means s is your variable and t is a constant. So what would the derivative of that with respect to s be? T. And then one of those t's cancels, and that's our derivative.
Can we just get 1 over s then?
Yeah, you just go 1 over s. And now you could go back and replace all your x's, right? You could replace all your x's with t squared plus 4s, and you could replace all your y's with natural log of st. And then what you would have is an expression that has s's and t's in it, right? That's only one of the partials. There's 2 of them. The other partial is to get this one here, right? So we need to get down to t. So what we do is the same game, except notice that to get to t, I've got to go down this branch and then down that branch, right? Here and then down the right side. And then here and then down the right side here. So I'm just going to write the formula. We're not going to actually compute it, all right? Because I think you get the idea. It's the tree is the more important thing. The partial of z with respect to t would be, let's see, the green branch down the left. Partial z with respect to x, partial x with respect to t, plus the green down the right side, partial z with respect to y, partial y with respect to t. And then you go figure out what each of those pieces are. Are you starting to catch on to this idea? Yeah? What? I'm sorry? Yeah, it's like a partial tree. Not a full tree, just a partial tree.
We're going to have t and s be dependent on 2 different things now?
Well, we're going to try and generalize right now. We're going to see if we can't generalize. Let's see how far I can push this. So let's say that z is some function that depends on n things, n different things. So I'm going to say x1, x2, x3, dot, 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 to xn. Now I'm using subscript because maybe z depends on 1,000 things, and I can't use letters anymore because I'm going to run out, right? So by using subscripts, I'll never run out. So f is some function of n variables. With me? Now, what if I tell you that x1 is some function of how many variables? Let's not use n because they don't have to be the same. Did you say m or n?
I said M.
M, okay, sorry, I heard n. Yeah, this could be a function of n variables, right? Let's call them, I don't know. Let's do S1, S2, right? S sub m, right? Something like that. And now x2, let's say that depends on how many, like, do you see we're going to start having some issues here, right? X2 could depend on, I can't use S again. Doesn't have to be the same variables, right? Right? T sub 1, T sub 2. How many of these do we have to have? Yeah, however many we want. T sub P. Yeah, see, do you see that this just starts to become a nightmare pretty quickly? Let me see if I can draw the tree, because the tree might help us see what's going on. Okay, first of all, Z depends on what? Okay, something like that, right? We got x sub n here, and we got x sub 1 here. Z depends on n different variables, right? And then each of those depend on whatever, right? So this x1 depends on, S1, S2, right, to Sm, right? And x2, where's x2? I'll just put x2 here, depends on its own variables here. The idea is that if you wanted to know the partial of z with respect to who knows what, okay? What you would have to do is first determine, does this variable you see here, does it appear in, like how many of these branches does it appear in? If this variable down here is the bottom of every branch, then it's going to be a straight derivative, right? Let's say everything z comes down to one variable, then this is going to turn from a partial to a straight derivative. But if the variable here is only appearing in certain branches, then to do this derivative, you're going to have to go down each branch that has that variable in it, right? So like let's say it goes ultimately down to some, I don't know, this branch, there could be more variables, right? Let's say way at the bottom here, we get to k. I haven't used k, right? Say we get to k. So let's say this is k. Then what you have to do is go down every single branch, and then you do whatever that derivative is, times that derivative, times that derivative, times that derivative, right? And then you say plus, and then you go see if there's any k's anywhere else. Does the method make sense to you? Because that's the more important thing. Just draw the tree and then go down your branches. I think I have a problem for us to do. No, I don't. Let me make one up. Let me make one up.
Favorite set of words followed by my least favorite set of words.
So what if I tell you this? Z is r squared plus st minus 3w. Then I tell you that r is equal to q to the third plus p. And then I tell you that, let's throw one more in there, plus k. There you go. And then I tell you that s is, let's keep it simple, q, p, k. And I tell you that w is q minus sine of p plus k. My first question to you, and I want you to think about this, and I want you to raise your hand if you think you have it. My first question, part A, what derivatives are possible? That's the very first thing. So take a moment and see if you can draw a tree on this real quick. Yes?
Is there a, you didn't give us T.
Oh, I forgot to give you T? Oh, I did forget to give you T. R, S. Oh, there's 4 up there. I forgot I put 4 up. 1, 2, 3. Oh, my. Okay, let's make this. Sorry, thank you for pointing that. Let's make T 1. Yeah. Let's just make it 4P. That's it. We'll keep it simple. Yeah, that'll actually throw a little layer of complexity to it also. All right, have you all tried drawing a tree?
Yep.
Yeah? What's at the top of the tree? Z. Okay, what variables does Z depend on? R, S, T, and W, right? So we're going to have 4 branches. 1, 2, 3, 4. R, S, T, W. Now, what does R depend on? Q, P, K, right? So 3 branches off of that. Q, P, K, Q, P, K. It's getting a little tight in here. Let me spread this out. Let me spread this out a little bit. Let me move my R over. R is over here. So R depends on Q, P, K. What does S depend on? Q, P, K again. All right, let's skip T for now. What does W depend on? Q, P, K, right? What does T depend on?
Q.
It's the same, but Q and K are 0.
Exactly. So this also depends. You could say that T depends on Q, P, K, but over here in the formula, it's almost like you have 0Q, 0K, right? That you could argue that T depends on Q, P, K now, right? Yes? That's an important thing to understand because you want your branches on the bottom to all have the same variables, or maybe just one variable at the end. So everyone understand the tree?
Yeah.
What derivatives are possible? Like, what are the things I could ask you for here? So who wants to volunteer the first one? Go ahead.
Since they all have the same variable, you would straight derivative all the way down.
Well, does Z depend on one thing and one thing only? Like, I can't just feed Z. If I feed Z the Q, is Z going to have a value? Like, or do you also need to know what P is? You would have to know P and K in order to get what Z is, right? So Z ultimately depends on more than one thing. So it can't be a straight derivative. It's got to be partials. So what's one of them?
Wouldn't it be partial of Z with respect to Q?
Yeah, I'm going to leave that up here.
One of our,
So yeah, one partial would be the partial of Z with respect to Q, because there's a Q down here, right? So you could go down and get to the Q branch, go down Q, go down Q, go down Q, right? That's not the only one. Go ahead.
Partial Z to
P, right? So that would be you go down all the branches that get you down to the P's, right? And then the last one would be partial Z respect to K, right? There are only 3 partial derivatives I could ask you for here, right? Let's write down the formula for at least one of these, all right? The formula. I'm not actually going to go through the work, okay? I'm just going to get the formula. That problem is just tedious. Again, the main idea here is to understand the tree and the diagram. And then all this is just calculus 1 stuff, right? Or, well, there's partials in there, so. All right, shall we fill out the tree? Hey, check this out. Maybe we can use a different notation. I don't know, I'm tempted to, but I'm a little scared. Because of space constraints, I could go z, r. Wouldn't that mean the partial z with respect to r? Just like when we started class, what did this mean? Partial of f with respect to x, right? So down this direction is partial z with respect to r. And then what down this branch? R with respect to q. How about here? R respect to p, R respect to k. Let's go down here. Partial z with respect to s, right? And then the three branches here. S with respect to q, S with respect to p, S with respect to k. I would prefer to use the partial notation, but it's just the space constraints I have right now. This would be partial z with respect to t. Let me finish off top. Partial z with respect to w. And then this would be t with respect to q, t with respect to p, t with respect to k. This would be w with respect to q, w with respect to p, w with respect to k. All right, I think for the sake of something interesting, let's do, well, let's just do the first one. Let's do the first one right there. We'll just do the first one. All right, so let's write the formula down for that one. And I actually do need to keep this. So I'm going to try and squeeze it in right here. If I want the partial of z, oh wow, I'm almost out of time. With respect to q, right, then I need to go down all the branches that get me down to q. So I need this and this. I need this and this. I need this and that. And this and that, right? So that's 4 branches. 4 branches I have to go down. So let me go down this branch first. It'll be partial z with respect to r times this one, partial r with respect to q. Plus, next one, come down here, partial z with respect to s, partial s with respect to q. That's this. 2 more. Partial z with respect to t times partial t. I know I'm out of time. Partial t with respect to q. 1 more. Plus, last branch, partial z with respect to w times partial w with respect to q. All right, that's what the derivative would be. I would have to go figure out all those things, right? There's one, remember the one that was interesting? This one right here? Right? That we, even though it looked like it was only dependent on p, we said, oh, it is dependent on p and q. Look at when we get to that right here. That's this piece right here, right? That's that. That partial t with respect to q, what would that be? 0, right? Do y'all see that? If I said take the partial of this with respect to q, it'd be 0. So what that's going to essentially do is kill off that piece of the derivative. Any variable at the end of the line that only depends on one of a few variables is going to kill off. Now, it won't kill off when you go down the p lines, right? For like the second partial right here, this one right here. That one, it wouldn't die off. Okay, do the homework for 11. This is 11.5, right? This is 11.5, chain rule. I expect by next class you will be done with all homework from 11.3 and 11.4. Don't worry about the 11.5 homework yet. We still have more to do in this section. We haven't answered the question about why that's a -1 yet. On the tangent plane, I will. And I'll, was there another one? You have a good day. What?
That's just the partial derivative homework, right?
Yeah, but then also the one after that, the chain rule, no, tangent plane problems. There's only a few of them, and they're pretty straightforward, but it's good practice for the partial derivatives.
Because I got partial